Okay, so here we talk about the synchrotron. In Chinese, this is called 回旋加速器. Okay. Yeah. So this is the diagram of a synchrotron. So it consists of an oscillator and then this area with two disks of a semicircle, and then there is a small gap in between. So from this dot S, okay, it is like the source. Okay, it will try to emit some emit some protons, and then it will just go like this. Or why it will be like that, like a spiral. Okay, so I will mention how it will be like that. Okay, so and there is a formula like the frequency of the oscillator. Okay, maybe I will talk about this a bit later. So let me talk about why it will be like that. So I just mentioned there is a gap. So let me draw it like this. Okay, and then suppose this is a source. And then there is some B field pointing out of the page, of course, in within this semicircle area, or in this area and this area. Okay, not in the gap. In the gap there's no B field. Okay, so yeah. Okay, so in this area we have the B field pointing out of the page. And then the source try to emit the proton with a vertical velocity. I mean the horizontal velocity. Okay, I mean pointing to the left side, not necessarily about that. Okay, so pointing this side. Okay, so this velocity and the B field are perpendicular to each other. So V cross B. Okay, we can see V cross B pointing upward. Okay, V cross B pointing upward, and then it is a proton. So yeah, positive charge. So there will be a force pointing upward. Okay, so there will be a circular motion, something like this. Okay, so you can see for this equation we have introduced last time. So the radius will be mv over qb. Okay, suppose we don't change the B field. We don't change the B field. And actually the Q doesn't change because it is a proton. Okay, it can be changed. And so as the mass, it can be changed also. Okay, so in this case, it means that the radius is proportional to the velocity. Okay, like this. Okay, so here, suppose this is a semicircle. So as much as this go back, this will be V. Maybe we can just call it V. V is okay. Okay, so in this area, there is no B field. But we can generate some E field. Okay, so this E field will change the direction frequently. Okay, in a specific frequency. This frequency is this one. Okay, so in this case, suppose the proton goes to this side, we will generate the E field pointing to the right side. And in that case, there will be a force Fe acting on the proton. So it will accelerate. Okay, so it will accelerate up to this point. The velocity will become faster. So I denote it as V prime. Okay, which means that V prime is larger than V. Okay, and then so here entering this region, there will be a B field and no E field, and then there will be a circular motion. But here V prime is larger. So R should be larger. Okay, so it becomes this one. go to here, it's still V prime. And then at this moment, we need to change the direction of the E field so that the E field pointing to the left side, okay, and then it makes the particle accelerate. There will be Fe pointing to the left side. So up to this point, it becomes V double prime, and then okay, at this point, V double prime is larger than V prime, and then entering this region, only B field and then no E field. So there will be a circular motion, okay, with a larger radius, okay. So in this case, we try to change the E field direction occasionally, and then we can eventually make the velocity of the particle become larger and larger, and then up to a point, and then it can shoot out. Yeah, so maybe up to this point, there will be a deflector plate, and then to make a beam, Okay, so that's how it works. Okay, so actually, there will be a limitation here, is that the energy of this synchrotron cannot be larger than 50 mega eV, cannot be larger than 50 mega eV. So the energy is not really large. The idea is that as much as we need to generate a large B field in this whole area and also this area, and in chapter 28, in chapter, I think we have not mentioned about the energy density yet. Maybe in chapter 30, But if you remember, for the UE is like 1/2 epsilon naught E squared. If you still remember in chapter 25, this is the energy density of the E field. So which means that if you need to generate the E field in a specific volume, then it takes energy. You need to spend energy to generate the E field. Similarly, for B field, the UB will be 1/2 mu naught and then B squared, something like that. Okay, so which means that if you need to generate a B field for this region and this region, then you need to spend a lot of energy. So in that case, as much as the region is large, so we cannot be able to provide a large B field there. And if the B field is not large, it will also limit the velocity. Because this is the radius. The radius is fixed. The largest radius is fixed. If the larger radius is fixed, if B field is small, then the V can only be smaller. Okay, so we need a larger B to make a larger output velocity. Okay, so that's why it limits the energy of the synchrotron. Okay, and we also talk about the frequency. The frequency is the frequency to change the direction of the E field. So this is pretty much it. And actually in the pure fit slide, we already mentioned the pure width. The pure width is like, or maybe I can just, the pure width. The pure width of the circular motion is 2 pi r over v, okay, 2 pi r over v. So I just try to recall it. T equals 2 pi r. R is mv over qb, and then over v. Okay, so v and v cancel. So it turns out to be 2 pi m over qb. Okay, so you can see that this is actually the reciprocal. So this is qb over 2 pi m, and this is 2 pi m over qb. So this f of C oscillator is nothing but the reciprocal of the pure width. Okay, so it turns out to be qb over 2 pi m. So we need to change the E field frequency. Okay. Yeah. So So here we will have another type of particle accelerator called a synchrotron. Okay. This is called 同步加速器. Okay. So we don't try to mention it very deeply. Yeah. But actually, the synchrotron is somehow like a ring. It's somehow like a ring. Okay. So we only need to generate the B field inside the ring rather than the whole circle. Of course, this is a circle with a gap, but yeah, actually this is two semicircles. So we need to generate the B field over the whole circle. But for the synchrotron, it's just like we only need to generate the B field inside the ring. But in this case, as much as we need to control R equals mv over qb, R over mv over qb. So in this case, as much as we need to fix the radius. Otherwise, we actually hope that the particle is actually like rotating inside this ring. Okay, if the radius is not controlled properly, it may just collide with the wall of the wing. So that will make the acceleration fail. Okay, so we need to fix the radius, and in that case, the mass doesn't change, the Q doesn't change, which means that we need to simultaneously try to increase the B field and try to make the V become larger. Okay, so we need more complicated control for the B field so that the particle won't collide with the wall of the synchrotron. Okay, so it will be able to provide a particle with higher energy. Okay, because this area will be smaller. We only need to provide the B field in the ring, so we can be able to provide a larger B. Okay, so it makes the V to be larger also. But the control will be more complicated. So in the Wikipedia, it mentioned that the beam is injected to the proton synchrotron booster. Okay, so yeah, just a front end. Okay, so try to accelerate to the particle to a specific level of energy, like 1.4 giga eV, and then this is the output of the synchrotron booster, and then it will output to a proton synchrotron, and then it push the beam to 25 giga eV. Okay, so just mention in the Wikipedia. So if you have interest, you can try to check it out. Okay. Yeah. Okay, so here let's take a look at a sample problem. Okay, so it says suppose a synchrotron is operated at an oscillator frequency of 12 megahertz and has a radius. Has a radius. Okay. R to be 53 centimeters. Okay, what is the magnitude of the magnetic field needed for the deuteratron? Deuteratron means it has one proton and one neutron. One proton and one neutron. Okay, so to be accelerated in the synchrotron, the deuteratron mass is this one. Okay. Yeah. So. Okay, so this is not difficult because we already know FOSC is like QB over 2 pi m. So we will be able to find the B field because it asks you what is the magnitude of the B field. So B field will be 2 pi m FOSC and then over QB over Q. Okay, so 2 pi m is this one, 3.34 times 10 to minus 27, and then times FOSC is this one, 12 times 10 to the 6th power, all over Q. Q is actually 1 proton, 1 neutron. Neutron doesn't have charge. Okay, so 1 proton is 1.6 times 10 to minus 19. Okay, so this is a 1.57 Tesla. Okay, Tesla. Okay, so this is pretty easy. We just need to plug in all the number to the equation for the oscillation frequency. Okay, so the next, what is the resulting kinetic energy of the deuteron? So we would like to calculate the velocity first, and then we can use a kinetic energy to be 1/2 mv squared to calculate the energy. So V is R QB over M. Okay, it originates from R equals mv over QB. Okay, and then we can get this. Okay, so we can just plug in the number. R is 53 centimeter, 0.53 times Q is still 1.6 times 10 to minus 19, and then times B is this value, 1.57 over 3.34 times 10 to minus 27. Okay, so this is 3.99 times 10 to the 7th power meter per second. Quite fast. More than 1/10 of the speed of light. Okay, so 4, 3. Okay, yeah. Okay, so actually K is 1/2 mv squared. So this is 1/2 times 3.34 times 10 to negative 27, and then times 3.99 times 10 to the 7th square. Okay, so this is 2.7 times 10 to negative 12 joule. Okay, so if we convert it into EV, so we divide this number by 1.6 times 10 to minus 19. Okay, so this number will become 17 mega EV. 17 mega EV. Okay, so just as I mentioned here, it is smaller than 50 mega EV. Okay, so this is pretty easy. Okay, so next we will talk about the magnetic force on a current carrying wire. Okay, I will consider this is a form of another form of the Lorentz force. The Lorentz force at the beginning of the chapter, the Lorentz force is Fb to be Q times V cross B, if you still remember. Okay, V cross B, Q times V cross B is the Lorentz force. Actually, this is another form of the Lorentz force. Okay, so here, what does it mean? Let's take a look at this figure. Okay, so for the figure A, okay, so we try to fix a wire here. So here and here is fixed. So these 2 points cannot be moved. But the wire is soft, so it may be able to bend. But at the first setup, we just provide the B view pointing out of the page. Okay, and there is no current. So okay, so the wire is still straight. Okay, but here, if we try to provide some current going from bottom to the top, okay, and the wire bend to the right side, and if we provide a current from top to bottom, then the wire will bend to the left side. Why it will be like that? Okay, so we can consider it like there are some positive charge going to the top. You may ask, oh, it should be a negative charge going to negative charge going in the opposite direction due to the whole experiment. But actually here, it doesn't really matter for this case. Okay, so I just make it like a positive charge going from bottom to top, following the current direction. Okay, so in this case, we have V pointing upward, and then B pointing to the out of the page. So V cross B using the right hand V cross B. Okay, so V cross B points to the right side. Okay, so FB points to the right side, like this. So this is actually a kind of Lorentz force. Okay, but for the third case, okay, so here, suppose we have a Q going from top to bottom. Okay, so this is V. Okay, so using right hand rule, V cross B, and then your thumb will point to the left side. So in this case, this is FB pointing to the left side. Okay. So I say this is another version of the Lorentz force, but of course here the notation are different. This is Q, this is I, this is V, this is L, this is V, this is B. Okay, so B still there, but yeah, QV becomes IL. Why it be like that? Yeah, so actually you can consider something like F. This is actually F, or maybe I just write it in a scalar form. Scalar form is not good, so I just keep the vector form. Okay, so Q, we have B there. Okay, we have V. Okay, V, we can actually change it to dl dt. Okay, so this is just like the displacement. Displacement is x. It's just like the length of the wire. Okay, and then we denote it as the vector. Oh, if I is pointing upward, okay, and then we will consider L is pointing upward. The magnitude is just the length of the wire. And then for this case, the L is pointing downward. Okay, L is pointing downward. Okay, follow the direction of the current. Okay, so it also mentioned that L is a length vector that has the magnitude L and is directed along the wire segment in the direction of the current. Okay, so we have this one. So we can just make it like dl dt. Okay, but actually if L doesn't change, we can just make it like something like a dq dt, and then L cross B, something like this. And then this one is actually the current, so it turns out to be I L cross B. And here actually the charge is moving. Okay, the charge is moving. Okay, so it turns out to be I times L cross B, I times L cross B. Okay, as much as L follows the direction of the velocity or the current. Okay, if we assume that the charge is positive, okay, so this velocity is the same, has the direction to be the same as the current. Okay, if it is negative, then V points to the opposite direction, but it turns out to be the same thing. Okay, so we just simply assume that the charge is positive, and then the velocity just follow the direction of the I. Okay, and L also follow the direction of the I. So this expression and this expression will give you the same idea, FB. Okay, so in this case, if wire is not straight, then we can simply just cut it into many segments. For each of the segment, we just calculate the FB to be I times dl and then cross B. So then within a small segment dl, then we can regard it as a straight wire. then we can calculate dl cross db and then times I all the way. Okay. So here we have a sample problem. So it says a strict horizontal length of copper wire has a current I through it. What are the magnitude and direction of the minimum magnitude magnetic field B need to be suspend the wire? That is to balance the gravitational force on it. The linear density of the wire is this number. Okay. So here we have a wire. We have a wire, and then L is pointing out of the page, which means that the I is pointing out of the page. Okay, so the wire is just putting there, and then of course there will be gravitational force mg. And as much as there is some current going outside, I to be 28 A, okay, going outside. Okay, so L cross B, B is pointing to the right side, so okay, yeah, it also asks you the direction, but of course this figure already show you the answer, because yeah, so pretend we are very lucky, we just assume that the B field point to the right side. Of course the B field must be perpendicular to the L, yeah, must be perpendicular, because it asks you for the minimum magnetic field. If it is not perpendicular, then there will be some B field which is yeah, I mean there will be some component of the B field which is parallel to the L, so which will not contribute to the force, so there will be a waste. So it asks you for the minimum magnetic field, which means that the B has to be perpendicular to the L, and of course you already have the gravitational force pointing downward, so which means that FB should be pointing upward to cancel it. So in this case, the B can be either pointing to the left side or the right side. So here, if we are so lucky, we assume that the B field points to the right side, so L is pointing out of the page, L cross B, so FB is pointing upward. Okay, so this is great. If B is pointing to the left side, so FB is pointing downward. Okay, have the same direction of the gravitational force, and there is no way to cancel. Yeah, so here we have the B field pointing to the right side, and in that case we have a ILB to be the FB. ILB, okay, as much as L and B are perpendicular to each other, so L cross B is nothing but L times B, and then equals M times G. Okay, so here we would like to also calculate the magnitude of the B field. So B will be like mg over IL. Okay, so we try to make it like m over capital L times g over I. Okay, because we don't have the mass of the wire, we only have the linear density of the wire, which is this is the mass over the length, so this is mass over the length, okay, times the gravitational yeah, the g, and then over I. Okay, so here this is 46.6, and then we need to change this to SI unit, so this is 10 to minus third power, okay, times 9.8 over I is 28. Okay, so this is 1.6 times 10 to negative second power Tesla. Okay, so this is pretty easy. Okay, so next we talk about the torque of on a current loop. Okay, so it's just like the motor. Okay, how a motor work. Okay, so here we have a large magnet bar. So this is okay, maybe like a U shape. Okay, this is the north pole, this is the south pole. As much as they are placing close together, it will generate a B field pointing to the right side, which is uniform, okay. So we assume that this setup will generate a B field which is uniform and then pointing to the right side. Here we try to place a current loop here. We try to fix the current loop in this with these two bar with a rotational axis. So this current loop cannot be moved but rotate. It can only be rotate either this direction or that direction. It depends on the direction of the current. Okay, so here let me see. We assume that the current is going like counterclockwise. This is counterclockwise. Okay, so in this case, let us see the force acting on the wire. Okay, so suppose for this one, for this one and this one. Okay, suppose the B field is pointing to the right side. The B field is pointing to the right side. Oh, let's see this one first. Okay, B field pointing to the right side. This is L. So L cross B, L and B point to the same direction. So there will be no force acting on this wire. Okay, so no force for this wire. And similarly, B and L points to opposite direction. So L cross B will be 0 either. Okay. Okay, so in this case, there will be no force acting on this side and this side. And for this one, L is pointing to that side. Okay, so L cross B. Let us see. L in this direction. B. Okay, so F pointing upward. Okay, for this one, L is pointing upward. F is pointing upward. And for this one, L is pointing to that direction. L cross B. So L cross B, and then the thumb will pointing backward. Okay, so we will get this is F, and as much as this axis is fixed, so in this case, this will rotate like this. So this is the mechanism of a motor. Okay. Yeah, so this is just a cross-section diagram of this one. Okay, so just so this. And here we will have a equation called tau to be NIAB sine of theta. Okay, so tau is actually the torque. And then NIA, N is the number of turn. Although it looks like there is only one turn, we can actually make it like multiple turn to increase the torque, so that the motor can rotate with a larger force like that. Okay, so this is a number of turn. N is the number of turn. So starting from this chapter, you try to be careful about this N, whether it is capital letter or small letter. If it is capital letter, it means the number of turn. If it is a small letter, if it is N, then it will be the density of the turn, which is like the number of turn per unit length. Okay, so be careful in this several chapter. We will have capital N or small n. Sometimes it will be capital N, sometimes it's small n. Okay, so here it is capital N, so it means the number of turn times the current times the area. Okay, so later on we will define this NIA to be a variable called the mu. Okay, so actually this mu is called the magnetic dipole will be n times I times A. N times I times A. Okay, so A is the area. Okay, it becomes an area vector. Okay, how to determine the direction of this one? Okay, so here we also use the right hand rule to determine. The direction. Okay, so here, suppose this is counterclockwise. We try to use our forefinger, follow the direction of the current, and then your thumb will pointing to this side. So which means that the area is pointing to this direction. Okay. Okay, so in this case, A is pointing to this direction. If the I is counterclockwise, you use your forefinger following the direction of the current. If the I is clockwise, then A is pointing downwards. Okay, so this is using the right hand rule to determine the direction. Okay, so this is mu, and then B. Okay, and then you can see a sine theta here. So when you see a sine theta, you can sense that it is something like the cross product. The cross product can generate this sine of theta term. Okay, so it turns out to be the torque is actually mu cross B. Okay, so A is pointing to this direction. Mu also points to the same direction, which means that mu also points to this direction. Okay, so then you can see that mu cross B is pointing into the page. Mu cross B in this figure, mu cross B is pointing into the page. Okay, so this is the direction of the torque. Okay, so the torque also follow the direction, follow the right hand rule. Okay, you use your thumb, follow the direction of the torque, and then your forefinger will be the direction of the rotation. So everything follow the right hand rule. Okay, so here we talk about a coil in a uniform magnetic field will experience a torque given by this tau to be mu cross B. Okay, just as what I mentioned. Here mu is NIA, and then A can be a vector. So this direction of the A follows the right hand rule. Okay, according to the direction of the current. Okay, direction given by the right hand rule. Okay, so this we have a tau equals mu cross B, similar to what we got for the E field. So in the E field, if you just place if you still remember in chapter 22, if I remember correctly, if you place a dipole, this is plus Q, this is negative Q. Okay, so it will swing back and forth. Okay, it will swing back and forth, and then also it will be like a tau equals mu cross E. At that time, did we use dipole moment, electric dipole moment? Yeah, somehow forgot. I forgot what symbol we use for the electric dipole moment, but it is something like that. Maybe still mu, or other thing. I really forgot. Okay, but anyway, here we also have the energy stored in the magnetic dipole in the magnetic field is U. This is the potential energy will be negative mu dot B, negative mu dot B. Okay, so similar equation as the electric dipole moment. So it means that if we have the magnetic dipole moment pointing to the same direction as the external B field, okay, so this B field is external. it is not generate external, not generated by this dipole moment, magnetic dipole moment. It is an external B field. So if we place this in the external B field, and then if the mu is pointing to the same direction as the B, then it has the lowest energy. Lowest energy means B mu dot B will be a positive number and maximize. Okay, and we take the negative sign. So this is the smallest value, which means the lowest energy. If mu and B points to opposite direction, then mu dot B will be like cosine 180 degrees. So this is the smallest value, and then taking the negative sign, it becomes the largest value. So this case has the highest energy. Okay, so let us finish this sample problem, then we can have a break. Yeah, so here it says a circular coil with 250 turns, and area A. Yeah, and area A is this value, and a current of 100 μA. The coil is reset in a uniform magnetic field of magnitude B, with its magnetic dipole moment initially aligned with B. Okay, in the figure, what is the direction of the current in the coil? Okay, so this is mu, this is B. Mu and B points to the same direction. Okay, so first it asks you what is the direction of this coil. Okay, so using the right hand rule, you start from pointing to the right side. Okay, the current will be something like this. Will be something like this. It's something like this. Okay, so this is the front, this is the back. So I just make it a little bit open to demonstrate all this. This is something like this. Something like this. hard to draw in a paper. Okay, so this is the direction of the current. As much as B is pointing to the right side. Okay, so for part B, how much work would the torque applied by external agent have to do the coil to rotate it 90 degrees from the initial orientation? So we try to rotate it something like pointing upward or pointing downward. Either it's 90 degrees from its initial orientation. So that mu is perpendicular to B and the coil is again at rest. Okay, so WA. WA will be U 90 degree minus U 0 degree. Okay, so 0 degree. Okay, so this is actually mu B cosine of 90 degree minus negative mu B cosine of 0 degree. Okay, so cosine of 0 degree is 1. Cosine of 90 degree is 0. This is 0. Okay, so this whole term vanish. Okay, so only remaining term is this one minus mu B times 1. So this is nothing but mu B. So it will be NIA times B. Mu is NIA. Okay, so mu NIA is 250 turns, and then times I is this one, 100 times 10 to the minus 6, and then times A is this one, 2.52 times 10 to negative 4, and then times B 0.85. So this is 5.36 microjoule. Okay, so this is pretty easy. And